The National Electrical Code, or NEC, does not permit multiple grounding electrode conductors, or GECs, to be connected to a single lug. NEC Section 250.32b specifically addresses grounding electrode conductor connections at detached buildings or structures. This section mandates that the grounding electrode conductor must be connected to the grounding electrode system as outlined in Section 250.50 and further requires connection to the equipment grounding terminal or grounding bus of the system. A critical stipulation within 250.32b is that the single connection to the grounding electrode system must be made at an accessible point inside the building or structure. The core principle here is a single, robust connection point for the grounding electrode conductor to the grounding electrode system. This single connection point is fundamental to ensuring effective grounding and fault current path. This means there should only be one connection from the grounding electrode conductor to the grounding electrode system. Consider a scenario with two grounding electrode conductors, one originating from exterior ground rods and another from an interior metallic water pipe. Connecting both of these grounding electrode conductors to a single lug on the grounding bus constitutes a violation of the NEC. The code necessitates that each grounding electrode conductor have its own dedicated lug or connection point on the grounding bus. To rectify this violation, the recommended approach involves ensuring each grounding electrode conductor is connected to a separate dedicated lug on the grounding bus. This adheres to the NEC requirement of a single connection for each grounding electrode conductor to the grounding electrode system. Now, let's delve into some additional considerations and related NEC sections to provide a more comprehensive understanding of grounding electrode conductor requirements. Grounding electrode system, section 250.50. This section dictates the electrodes that must be bonded together to form the grounding electrode system. These electrodes include metal underground water pipes, metal frames of buildings and structures, concrete encased electrodes, ground rings, and rod and pipe electrodes. Section 250.50 is the foundation for what constitutes an effective grounding electrode system. Sizing grounding electrode conductor, section 250.66. The size of the grounding electrode conductor is determined by the size of the ungrounded service entrance conductors. Table 250.66 provides guidance on the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The grounding electrode conductor must be of sufficient size to handle potential fault currents. Protection of grounding electrode conductor, section 250.64. This section covers the requirements for the physical protection of the grounding electrode conductor. The grounding electrode conductor must be securely fastened and protected from physical damage. Where exposed to physical damage, the grounding electrode conductors shall have supplementary protection. Bonding jumpers, section 250.92. Bonding jumpers are used to ensure electrical continuity and conductivity. Bonding jumpers are crucial in maintaining a low impedance path for fault currents. Grounding electrode conductor connections, section 250.70. This section specifies the methods for connecting the grounding electrode conductor to the grounding electrode. Connections must be made using listed connectors or by exothermic welding. Proper connections are vital for ensuring a reliable grounding system. Resistance of grounding electrode system, section 250.53 ATWO. This section addresses the requirements for the resistance of the grounding electrode system. The resistance to earth of a single electrode must not exceed 25 ohms. If the resistance exceeds 25 ohms, a supplemental electrode is required. Multiple electrodes are often necessary to achieve the desired low resistance. Common grounding electrode, section 250.58. Where multiple services or systems are supplied by a single grounding electrode, a common grounding electrode is permitted. This simplifies the grounding system and ensures equipotential bonding. Ground clamps, section 250.8. Ground clamps used for connecting grounding and bonding conductors must be listed for the specific purpose. The use of improper ground clamps can compromise the integrity of the grounding system. Underground service cable, section 230.30. For underground service cables, the grounded conductor must be insulated. This is particularly important in preventing corrosion and maintaining the integrity of the grounded system. Neutral conductor, section 250.24. The neutral conductor must be connected to the grounding electrode at the service entrance. This connection ensures that the neutral is at or near ground potential. Separately derived systems, section 250.30. For separately derived systems, such as generators or transformers, a grounding electrode system must be established. This grounding system must comply with the requirements outlined in Article 250. Grounding and bonding equipment, section 250.130. Non-current carrying metal parts of equipment must be grounded. This grounding helps to minimize the risk of electrical shock. Ground fault circuit interrupters, section 210.8. Ground fault circuit interrupters, or GFCIs, are required in specific locations to protect against electrical shock. GFCIs detect ground faults and quickly de-energize the circuit. Surge protective devices, section 285. Surge protective devices, or SPDs, are used to protect electrical equipment from transient voltage surges. SPD must be properly grounded to function effectively. Equipotential bonding, section 680.26. In swimming pool areas, equipotential bonding is required to minimize voltage gradients. Equipotential bonding helps to prevent electrical shock hazards. Agricultural buildings, section 547.9. In agricultural buildings, specific grounding and bonding requirements apply. These requirements are designed to address the unique hazards present in agricultural environments. Healthcare facilities, section 517.13. Healthcare facilities have stringent grounding and bonding requirements to ensure patient safety. These requirements are critical for minimizing the risk of electrical shock in sensitive areas. Industrial control panels, section 409.110. Industrial control panels must be properly grounded and bonded to ensure safe operation. Proper grounding and bonding are essential for preventing electrical hazards. Flexible metal conduit, section 348.60. Flexible metal conduit, or FMC, must be properly grounded. FMC can serve as an equipment grounding conductor if it meets specific requirements. Liquid-tight flexible metal conduit, section 350.60. Liquid-tight flexible metal conduit, or LFMC, must also be properly grounded. LFMC can be used as an equipment grounding conductor under certain conditions. Electrical metallic tubing, section 358.60. Electrical metallic tubing, or EMT, can serve as an equipment grounding conductor. EMT provides a continuous metallic path for fault currents. Galvanized steel rigid conduit, section 344.60. Galvanized steel rigid conduit can also serve as an equipment grounding conductor. Rigid conduit offers excellent mechanical protection for conductors. Aluminum conduit, section 344.60. Aluminum conduit can be used as an equipment grounding conductor under specific conditions. Aluminum conduit must be properly installed to ensure effective grounding. Cable trays, section 392.7. Cable trays must be properly grounded to ensure electrical safety. Cable trays provide support and routing for cables. Busways, section 368.17. Busways must be grounded to provide a low impedance path for fault currents. Busways are used for distributing power in industrial and commercial settings. Receptacles, section 406.4. Receptacles must be properly grounded to ensure electrical safety. Grounded receptacles provide a path for fault currents. Lighting fixtures, section 410.44. Lighting fixtures must be grounded to minimize the risk of electrical shock. Grounding of lighting fixtures is essential for safety. Appliances, section 422.16. Appliances must be grounded to protect against electrical shock hazards. Grounding of appliances is a critical safety measure. Motors, section 430.12. Motors must be properly grounded to ensure safe operation. Grounding of motors is essential for preventing electrical hazards. Transformers, Section 450.10. Transformers must be grounded to provide a low impedance path for fault currents. Grounding of transformers is critical for safety. Capacitors, Section 460.10. Capacitors must be grounded to protect against electrical shock hazards. Grounding of capacitors is an important safety measure. Generators, Section 445.14. Generators must be properly grounded to ensure safe operation. Grounding of generators is essential for preventing electrical hazards. Data processing systems, Section 645.15. Data processing systems have specific grounding requirements. These requirements are designed to ensure reliable operation. Communication systems, Section 800.100. Communication systems must be grounded to protect against electrical surges. Grounding of communication systems is essential for safety. Radio and television equipment, Section 810.20. Radio and television equipment must be grounded to protect against electrical surges. Grounding of radio and television equipment is important for safety. Community antenna television systems, Section 820.93. Community antenna television systems must be grounded to protect against electrical surges. Grounding of these systems is essential for safety. Optical fiber cables, Section 770.100. Optical fiber cables entering buildings must be grounded. Grounding of optical fiber cables is important for safety. Class 1, Class 2, and Class 3 remote control, signaling, and power limited circuits, Section 725.43. These circuits must be grounded under certain conditions. Grounding of these circuits is important for safety. Fire alarm systems, Section 760.35. Fire alarm systems must be grounded to ensure reliable operation. Grounding of fire alarm systems is essential for safety. Solar photovoltaic systems, Section 690.41. Solar photovoltaic systems have specific grounding requirements. These requirements are designed to ensure safe operation. Wind electric systems, Section 694.40. Wind electric systems must be properly grounded to ensure safe operation. Grounding of wind electric systems is essential for safety. Fuel cell systems, Section 692.44. Fuel cell systems have specific grounding requirements. These requirements are designed to ensure safe operation. Electric vehicle charging systems, Section 625.28. Electric vehicle charging systems must be grounded to protect against electrical shock hazards. Grounding of these systems is an important safety measure. Temporary wiring, Section 590.4. Temporary wiring installations must be grounded to ensure electrical safety. Grounding of temporary wiring is essential for preventing electrical hazards. Hazardous locations, Articles 500 through 516. Hazardous locations have specific grounding and bonding requirements. These requirements are designed to prevent explosions and fires. The single connection requirement for grounding electrode conductors is not arbitrary, it's a deliberate measure to ensure a reliable, low-impedance ground fault path. When multiple conductors are connected to a single lug, the effectiveness of the connection can be compromised. The NEC prioritizes a direct, dedicated connection to facilitate the rapid clearing of ground faults. In summary, while it might seem convenient to connect multiple grounding electrode conductors to a single lug, it is a clear violation of the NEC. Adhering to the code's requirement for individual connections ensures a safer and more reliable electrical system. Always consult the latest edition of the NEC and local amendments for specific requirements in your jurisdiction. The grounding electrode conductor should be continuous from the grounding electrode to the grounding bus. Splices are generally not permitted in grounding electrode conductors unless they are made using irreversible compression connectors listed for the purpose or by isothermic welding. The purpose of this rule is to ensure a permanent and reliable connection. The grounding electrode conductor should be installed in a manner that protects it from physical damage. Where the grounding electrode conductor is exposed to physical damage, it should be enclosed in rigid metal conduit, intermediate metal conduit, rigid non-metallic conduit, electrical metallic tubing, or cable armor. The type of protection should be appropriate for the environment and the degree of physical stress to which the conductor is likely to be subjected. The grounding electrode conductor should be securely fastened to the surface on which it is carried. This helps to prevent the conductor from becoming loose or damaged. The fasteners should be appropriate for the type of surface and the size of the conductor. The grounding electrode conductor should be installed as directly as practicable. Unnecessary bends or loops in the conductor can increase its impedance and reduce its effectiveness. The conductor should be routed in a way that minimizes its length and avoids sharp bends. The grounding electrode conductor should be arranged so that it is accessible for inspection and testing. This allows electricians to verify the integrity of the grounding connection and to measure the resistance of the grounding electrode. The grounding electrode conductor should be identified by marking or labeling. This helps to ensure that the conductor is not accidentally disconnected or damaged. The marking or labeling should be durable and easy to read. The grounding electrode conductor should be connected to the grounding electrode in a manner that provides a permanent and reliable connection. The connection should be made using a listed connector or by exothermic welding. The connection should be protected from corrosion and physical damage. The grounding electrode conductor should be connected to the grounding bus in a manner that provides a low impedance path to ground. The connection should be made using a listed connector or by bolting the conductor directly to the bus. The connection should be protected from corrosion and physical damage. The grounding electrode conductor should be inspected and tested periodically to ensure that it is in good condition and that it is providing a low impedance path to ground. The inspection and testing should be performed by a qualified electrician. The results of the inspection and testing should be documented and kept on file. When replacing or upgrading a grounding electrode system, it is important to ensure that the new system complies with the requirements of the NEC. The new system should be properly designed, installed, inspected, and tested. It is also important to ensure that the old system is properly disconnected and removed. When working on a grounding electrode system, it is important to take appropriate safety precautions. This includes wearing appropriate personal protective equipment such as gloves and eye protection and using properly insulated tools. It is also important to energize the electrical system before working on it. If you are not qualified to work on a grounding electrode system, you should hire a qualified electrician to do the work. A qualified electrician has the knowledge, skills, and experience necessary to install and maintain a grounding electrode system safely and effectively. A grounding electrode system is a critical safety component of an electrical system. It is important to ensure that the grounding electrode system is properly designed, installed, inspected, and tested. By following these guidelines, you can help to ensure that your electrical system is safe and reliable. The National Electrical Code is updated every 3 years. It is important to stay up to date on the latest requirements. You can purchase a copy of the NEC from the National Fire Protection Association, or NFPA. You can also find information about the NEC on the NFPA website. The grounding electrode system is an essential part of any electrical system. It provides a path for fault current to flow back to the source, which helps to protect people and property from electrical shock and fire. A properly installed and maintained grounding electrode system is a critical safety component of any electrical system. The grounding electrode conductor is the conductor that connects the grounding electrode to the grounding bus. The grounding electrode conductor must be sized according to the size of the service entrance conductors. The grounding electrode conductor must be made of copper or aluminum. The grounding electrode conductor must be protected from physical damage. The grounding electrode conductor must be installed in a continuous length, without splices or joints. The grounding electrode conductor must be connected to the grounding electrode in the grounding bus using approved methods. The grounding electrode must be a rod, pipe, or plate that is buried in the ground. The grounding electrode must be made of copper, steel, or other approved material. The grounding electrode must be of sufficient size and length to provide a low impedance path to ground. The grounding electrode must be installed in accordance with the requirements of the NEC. The grounding bus is a metal bar or plate that is used to connect the grounding electrode conductor to the equipment grounding conductors. The grounding bus must be sized according to the size of the service entrance conductors. The grounding bus must be made of copper or aluminum. The grounding bus must be securely mounted to the electrical panel. The grounding bus must be accessible for inspection and testing. The equipment grounding conductors are the conductors that connect the non-current carrying metal parts of electrical equipment to the grounding bus. The equipment grounding conductors must be sized according to the size of the circuit conductors. The equipment grounding conductors must be made of copper or aluminum. The equipment grounding conductors must be installed in accordance with the requirements of the NEC. The grounding electrode system is a critical safety component of any electrical system. It is important to ensure that the grounding electrode system is properly designed, installed, inspected, and tested. By following these guidelines, you can help to ensure that your electrical system is safe and reliable.